All right. Okay, so let me just recap very, very quickly. So again, what we want to deal with today are these localization problems where you want to describe the transports of, through disordered media. And the first topic that we want to address is the question of the conductivity. Okay, so let's just okay. Let me just share again my screen. So that's the setup that we want to study. Okay, so we want to look at the Ohm's law, and which relates typically the voltage through the current I via this relation. And the question is how can one compute this R? And typically this R is related to what is called the conductivity via these relations, where this L of S is just a simple geometric factor of your sample. Now, as I said, so in general, computing sigma is an out of equilibrium problem because you have a current through your system. And this is in general quite a complicated problem. Okay, so computing sigma is generically a hard non-equilibrium StatMech problem. And in general, there is no general theory to do that. However, there is a well-known approach that you can start with, which is a kind of phenomenological approach, which is the so-called root theory, which we have certainly heard of quite some time, or already quite some time ago, maybe at high school. And what this root theory tells you is very simple: is that you are just modeling the electrons and the transport of electrons via collisions with either phonons or impurities. And eventually, what you obtain is that sigma essentially takes this form in this simple model, which I'm just writing it this way here, which take this form where sigma is just n times e squared tau by m. So e squared and m are respectively the charge and the mass of the electrons, and these quantities there. So n is just the density of carriers. So this is just here the density of electrons in your system. And the important parameter that actually characterizes the disorder is this tau here, which is called the mean free time. And which is, of course, related to the mean free path. And this is essentially the mean free time between two collisions. So that's what this Drude's theory is about. And these collisions can happen, say either, so if you are describing the charge transports in a material, this can be, for instance, with phonons, if you have a lattice or a crystal, or it might be also, of course, with impurities, and that's really what happens in the presence of disorder, which is what we want to study. Now, it's clear that when you look at that, it's clear that the more you have, the more impurities you have in your sample, of course, the shortest will be this mean free time between successive collisions, and eventually that means that the conductivity will decrease if the density of impurities increases. Okay, so that means that typically what happens is that sigma will decrease when the disorder increases. Okay, disorder here means impurities basically. So essentially two types of different behavior. So you could expect two types of different behaviors, especially when you are a statistical physicist. When you plot, say, sigma as a function of the disorder, so I'm plotting here sigma as a function of the strength of the disorder. Okay, when I'm saying here disorder, I mean strength of the disorder, of course. So either you might have a smooth decreasing function, that means that the sigma might go to zero as the strength of the disorder grows, but still it goes to zero only asymptotically. So that's one first situation that you may encounter. Or another situation that may happen is that as sigma, if you plot sigma again as a function of disorder, so that's the second situation that may occur. What may instead happen is that sigma actually may become exactly zero at a finite value of the disorder. And in this case, essentially what will happen is that you may have a phase transition in this case where at low disorder, the conductivity would be finite, and therefore you would have, say, what we call usually a metal. On the other hand, if the disorder is sufficiently high, then transport will be much, the conductivity will be strictly zero. And eventually what you would get here is that you will have an insulator. Okay. Now maybe one remark here, one quick remark is that, of course, even if you have this kind of situation where sigma is zero, this does not mean that that really that say I is zero itself. Okay, it's just that if sigma is infinite, so sorry, if sigma is zero, so that means R is very big. It just means that instead of having a linear relation, you might have a more complicated relation. Okay, so that means that you will not be proportional to I, but for instance, it might be proportional to I square, or when I is small. So you might break, if you want, this linear relation. So that's really what it means. So the big question that you have to face, and that especially theoreticians have asked for quite some time, is whether you have this scenario or that scenario. So in other words, the big question is whether you have a phase transition, or do you simply have a simple crossover when where sigma is high towards a region where sigma is much smaller. Okay, so that's really the question that that has been there for quite some time. And in fact, the first who studied or proposed this question is Phil Anderson in '58. Probably have heard about Anderson, who got the Nobel Prize and passed away rather recently. But he was the first to address this question, and we will talk about the kind of model that he has proposed in a while. But it's fair to say that since then, the question of this question, which is nowadays known under the name of localization, we will understand more why and what it means. But this question actually has been the subject of a huge amount of papers, of studies, both in physics and in this case, in fact, both theoretically and experimentally, as you can imagine, but also in mathematics. Okay, this has been really a central question at the interface between probability and theoretical physics, and this is actually still quite lively subject. So This is one point of view. So that's the point of view of transports, and that's how it sort of was raised in physics. There is a dual point of view, which is quite interesting, and unfortunately, I will not have time to elaborate too much on that perspective. But it's quite important to see how it is related to that question, which is the question of diffusion. Okay, so when we talk about transports, it's quite natural to have these properties in mind. And what I would like to discuss here is a kind of dual question, which is the case where you don't have any driving force, so you forget about applying voltage in your system, but you consider the case which, okay, I called dual in some way. The dual situation, say where E is equal to 0. And in this case, what happens is that the particles, in this case electrons, what will happen is that typically the electrons will diffuse. Okay, so they have a kind of random motion. And in particular, that means that what I mean by diffusion is really the fact that if you compute the mean square displacement, okay, so that's if I compute r squared t, average over all the possible noise, which might be thermal noise, which might be even the disorder here. This might also be the initial conditions or whatever. If you have diffusion, then that means that at large time, this will grow linearly with t. Okay, that's the definition of diffusion. And the coefficient in front of that is usually denoted as 2d, and d here is the diffusion constant. Okay. Now, it turns out that d and sigma, so the diffusion constant and sigma the conductivity, they are related, and that's why I call this dual situation. They are related by a fluctuation dissipation theorem, if you want, which relates, on the one hand, the fluctuations, the intrinsic fluctuations, if you want, of the system in the absence of any external driving force, to the linear response of the system in the presence of a small external driving force. And in this case, that gives you a relation between d and sigma, so fluctuation dissipation theorems. Some of you have heard about such relations, but I will not elaborate too much on that. But fluctuation dissipation theorems implies a relation between d and sigma. And let me just write it. This is sometimes called so this is just d equal kbt divided by ne square times sigma. Okay, so this is just sometimes called Einstein or Kubo formula. This has to do with the linear response of the system. But you see that the conductivity that I was talking about before has actually a direct consequences on D and on the diffusion property of the system. So if I just want to make a connection, say, between what I was saying before in this context here, basically, how does this translate in terms of the diffusion? Well, it simply says that so this relation will essentially tells you that basically, if you have an insulator while you have sigma equal to 0, and that means d equal to 0. So that means that you have no diffusion. And in other words, in this case, one talks about localized states. So if you look at particles and the way they move around, that tells you, because d is equal to 0, that says that particles are localized. Okay, so that means that typically they will stay in a confined region of space without exploring the full sample. And as a matter of fact, they wouldn't be able to carry current or to carry charges, and therefore sigma eventually will be equal to 0. Now, on the other hand, sorry, if you have a metal, then what happens is that, well, sigma is strictly positive, and therefore d also will be strictly positive, and you will have diffusion. Okay, so so that's why we call this phenomenon localization, simply because disorder is able to localize the positions of the particle, and eventually in the quantum mechanics language, we will see that disorder is able to localize the eigenfunctions of your state, the eigenfunctions of your particles in a given region of space, namely close to the impurities. Okay. So again, maybe this is, as I said before, even if you are in the localized phase, that means that d is equal to 0. Okay, so that means that if you look at r square, well, it will not grow anymore as t. Okay, so that means that r square divided by t in the large T limit will go to 0, but r square itself might still diverge. And typically what happens, for instance, in one dimension, if you look at this famous Sinai model, where you look at a simple case where one particle jumps to the right or to the left with probabilities which are different for the going to the right or to the left, but on top of that, which are different from site to site. Okay, so that means that on each site, you have a given probabilities. So the system is disordered in that sense, that the rates or the probabilities may depend on the location of the particles. Then in this case, what happens is that, at least in the symmetric case, what you would observe is that r square of t does not go as t, but goes like to the log of t to the power 4. Okay, so that means that the particle is still moving, right? But nevertheless, it moves much slower than diffusively. Okay, so that's what we mean by localized, if you want, in this context. Okay, are there questions? Again, I can't. I mean, I don't read the chat. So if there are questions, please tell me. Okay. And is it fine? Can you read correctly what I write on the slides?
Yes, it's good.
Okay. Okay. So yeah, maybe one point that I should say, I mean, about the whole lecture is that, as you will see, what we will, and this is a bit maybe at variance with what we did before. This lecture will be relatively qualitative, and what I want to tell you is to give you is a kind of overview of the subject, because it's a central theme in disordered systems. But entering into the details would be too demanding. In fact, there are courses like the one by Christophe Texier and Cheroret about these problems. But so here I just want to give you a kind of overview and touch upon some topics which are related to what we have heard about, like random matrices, that will come a bit later. Now, what I want to discuss is the effects of dimensions. It turns out that when looking at localization problem, it turns out that the dimensionality of your system actually plays a role. Okay, so dimensions do matter. So what it means is that and as you would expect somehow, what we know from our experience of statistical mechanics, we know that in low dimensions, typically the fluctuations are very strong. Okay, so that's the case, for instance, in the Ising model, right? So in low dimensions, we would expect that the fluctuations are strong. Here, we are talking about, I mean, of course, we could think about thermal fluctuations. Here, of course, I have in mind mainly the fluctuations which are due to the disorder. Okay, but these fluctuations, they might be in principle thermal or due to the disorder. Okay. So again, in statistical mechanics, you know that if you look at the Ising model, for instance, if you look at d equals 1, we know that the fluctuations are strong enough such that the critical temperature is 0. So that means that at finite temperature there is no ordered phase, and as soon as you add a little bit of fluctuations, they destroy completely the order. Okay, so that's what they do. Okay, so that's what fluctuations actually may do. Is that they can actually destroy long-range order in the system. They can destroy the ordered phase. Okay, so that's now. It turns out that this is a bit. I mean, a similar scenario happens in the localization problem, and essentially what happens is that in low dimensions, as soon as you put some disorder, then the disorder will destroy any kind of order. And in this language, this means that all the particles becomes localized as soon as you have some infinitesimal disorder in your sample. Okay, so now dimension is low enough. Low dimension here in this case means basically d equals 1 and d equals 2. So in other words, in d equals 1 and d equals 2, an infinitesimal disorder actually leads to localization. So sigma is 0, conductivity is 0, and diffusivity is also 0 in this case. The same is true, in fact, in d equals 2. Although if you really look at more refined definition of localization, you might find that in d equals 2, localization actually happens in a weaker form in d equals 2, but still essentially the effects are the same, such that all the states are localized. Now only in d equals 3 and higher, so say in d equals 3, you will have actually a metal insulator transition as a function of the strength of the disorder. So we will see a bit later the phase diagram that you have in this case. It is relatively rich. But roughly speaking, this means that if disorder is small, then the states will not be localized. We say that they are extended. We will see what it means more precisely in a minute. But if disorder is big enough, then the states becomes localized. Okay, so and you might have indeed a transition between a metal and an insulator. Okay, so we will try to characterize a bit more precisely what we mean here in in the context of some microscopic models, and basically in what is called the Anderson model. But before that, I just want to mention that what I will discuss here, namely in the context of Schrodinger equation, essentially, that means the localization of quantum waves, is actually more general. And in fact, localization in general and localization properties are actually much more general than the problem that I will discuss here in the context of quantum particles. But basically, localization may actually occur as soon as you have classical waves, or say waves in general, that would propagate in a disordered media. Okay, and that's actually a situation which is quite frequent in physics. But I just mentioned it, and just to say that this is not something which is restricted to quantum systems, but actually localization occurs also for classical waves propagating in disordered media. So this might be, for instance, sound waves. You might also think about light itself. So this is actually much more general. There is a huge literature on this problem. But today I will mainly focus on these metal insulator types of transition. But keep in mind that this is much more general. And again, I know that Christophe Texier and then Cheroré actually cover these questions in more detail, but I will not have time to mention or to discuss this in more than that. Okay, so that's a kind of very broad overview of what the topic of localization deals with. And now I would like to be a little bit more precise and present to you some models that have been introduced since Anderson, in fact. And I want to discuss microscopic models. Having again in mind the problem of a quantum particle in a disordered potential. Okay, so let's start with the most natural model that you would like to write when you start from a Schrodinger equation, which is a continuous model. So what I will just have is basically one electron in a potential V of R, and this V of R is a random potential. Okay, so I have one electron. I will discuss here mainly the question of the localization properties of a single particle. Okay, there is currently a very huge activity on what is called many-body localization, which has to do with the problem of interacting particles in the presence of disorder, which is a very active subject. But today I will focus on the simplest example where I have one electron in a potential say V of R. Okay, so that means that what I really want to look at is the Schrodinger equation. Okay, so how does it look like? Well, we haven't talked too much about quantum mechanics in this course, but it is a very simple problem here. Okay, so it's just a single electron or single particle, and psi is just, say, a function of RD. Okay, so it lives on this d-dimensional space. And what V of R is, the generic model that you might think of, is that V of R models the presence of impurities. Okay, so the random potential there are various ways, of course, to introduce these potentials V over R. But for instance, a natural way to introduce it is to imagine that you have, say, impurities in your sample, which are, say, just randomly placed in your sample, and you will model each impurity with a delta potential. Okay, so this is typically the model that you adopt in quantum mechanics to model the presence of a single impurity, which might be repulsive or attractive. So that means that you will have a collection of such, say, so you will say index each of your particles by, so imagine that your origin is there, and you will label the positions of your particle by, say, xn, and these xn here are random variables, and the potential that you are considering here is this V over R, which would be just the sum of delta potential. Okay, so you would have this kind of potential here. I'm not saying that this is the only possible way to model random impurities, but that's a quite reasonable one if you have such a model in mind. Okay, and of course, the point here is that the important point is that this an and xn, both of them, they are random variables. Okay, and to be more precise, they are actually quenched random variables. Okay, so that means that, suppose that even if you are at 0 temperature and you would like at the ground state of your system, so you would still have some quantum fluctuations in your model. So you would like to perform some averages over the quantum fluctuations, but keeping these variables here, an and xn's, as quenched. That means fixed ones. Okay, and then eventually you would like to perform some average over these quenched random variables. And to do that technically, you would probably need to go through these, for instance, replicas and so on, which of course can be useful also in this context. Now, what happens here when you, and the idea, of course, is that now you want to solve this problem. Okay, so it's quite complicated problem. So this is the dynamical version, but you can think only later on we will actually focus on the fixed energy problem, where you just look at the eigenfunctions of this operator. But what will happen, because you know quantum mechanics, is that the disorder basically will induce some multiple scattering through these impurities. And basically the question is, so that they will induce some interferences, which is due to the diffusion of this wave in this disordered medium. And the question is whether these interferences from these various impurities, whether these interferences are constructive or destructive. Okay, so that's really the question that that we are after. So let me just write it. That we want to really to characterize is whether these interferences due to multiple scattering by the impurities the question is whether these interferences are constructive or destructive. Okay, so that's really the question. So as a remark, if you just consider, for instance, what you know, what happens in a crystal, you could think of such impurities, but which have a periodic structure. So in this case, for instance, if you have some periodic scattering, then you know that there is the Bloch theorem that tells you that in this case you will still have kind of ordered wave in some sense. And in this case, we know that from Bloch theorems, we know that these interferences are actually constructive in that case. But in the presence of disorder, this question is actually much more, much more complicated, and the answer is much less obvious. So this is one type of model. This is a continuous model that we have in mind, and somehow that's true that when you start with quantum mechanics, that's certainly the most simplest one, most natural one. But it turns out that it's quite difficult to solve. And in many cases, in condensed matter, probably you have already seen that before, it's quite useful to have a lattice model which allows to make some progress analytically. And that's what essentially Anderson proposed in his famous papers. And that's this lattice model that I want to discuss with you. Okay, so just try this one. Okay, can you hear me correctly?
Seems to be fine for me.
Is it fine? Yeah. Okay. Yeah. By the way, are there questions at this stage, or is it clear? No question. Okay. So let's continue then, and let's go to the lattice model, which is sometimes called Anderson model. Okay. So let me just illustrate it in 2D because it's always simpler. Okay, so instead of having a particle that moves in a continuum, say in R, I will now consider the case where my particle just lives on the sides of a lattice, say of ZD, and that means that typically my particle may live on the vertices of this lattice. Okay, and so the particle is a quantum particle, but it lives on ZD. Okay, and that means that the positions are just labeled by an integer, I'll say a vector Rn. Okay, so n is the label of the site, and the of course now you will also discretize your wave function. So instead of being a function, it will become a vector. Okay, so this approximation is well known in condensed matter, and this is called tight binding model, or tight binding approximation. En français, c'est ce qu'on appelle la liaison forte, modèle de liaison forte. So what it means is that now your wave function psi will become a vector, say with capital N components. So you have capital N sites. Okay, so this is the total number of sites. Typically, what you would consider, and that's what we will have in mind in the following, you will consider the case where you have periodic boundary conditions. So you have a finite n, but periodic boundary conditions. And you want to have a discretized version of the Schrodinger equation. Okay, So let's just look at the simple example of the 1D case, just to fix the ideas. So in d equals 1, okay, so my equation would be, well, let's look at the, okay, now I should say also something that from now on, I will actually look at the time independent Schrodinger equation mostly. I will mostly focus on that. So I look at essentially it means that I look at the case where the particles have a fixed energy. Okay, so E is fixed, and I just simply look at this Schrodinger equation. And I want to have a discretized version of that. Fine. So what I need really to do is to write a discretized version of this Laplacian. So let's do that. Well, what it gives me is simply these things, right? So this is just, so I don't touch this guy, but then this one will be psi of n plus 1 plus psi of n minus 1 minus 2 psi n, okay? And then I will have the disordered potential, Vn, also the potential itself, psi n, is equal to E times psi n. All right? Now, of course, what we have in mind here is that what the problem that we really want to discuss is the case where V of R is a random, okay? Before, I just showed you this example where V of R would be the sum of delta functions, but it could be, you could choose it to be slightly different. For instance, you could think of it as a random function. That would be, for instance, a Gaussian random variables with short range correlations. Or this could be a random variable with a uniform distribution, say between minus V0 and plus V0. And that's what we'll consider later on. But of course, what I want to say is that because V of R here is random, then this V of n here is of course also random. Okay. Now, what is usually done in this approach is to notice that, you see, I have this diagonal term here, which is minus 2 psi n. Basically, what we usually do in the context of localization is that we absorb this term in the energy there. So that means that you can also write it as follows. We really look at the simplest model to write. Okay, so that's what we typically have. And here what you get is simply E minus 2 h bar square divided by 2m times psi n. And what I want to say is that, okay, what you do is that this guy is just a kind of renormalized energy, right? It's just a shift, global shift of the energies. So let me just call it epsilon, okay? So that means that I can roughly, I can again equivalently, sorry, write it like that. And that's what, so I call this minus h bar square over 2m minus t. And this is what I have. This is just a stupid rewriting, but it's just a remark here that, of course, the difficulty is really to understand what happens when this Vn becomes random, okay? The first question that you could ask is what happens if I have no randomness, but simply a simple diffusion, okay? So that means that I only have what I would call this hopping term, okay? Because this is a term that basically allows to hop from the site n to site psi n plus 1 or psi n up n minus 1. So these are the terms that in this tight binding approximation we usually call hopping terms. while this one is really the term which is due to the disorder. But let's just remind what happens in the absence of disorder. Okay, so if you just have hopping, that means that if you just look at the Schrodinger equation with on the discrete lattice and say with periodic boundary condition, if you want, then in this case I will need this later, this result later. So it's just a remark. I will not prove it, but it's very easy. Is that if Vn is 0 for all n, well, then it's clear that it's easy to compute the eigenfunctions or the discretized version of the eigenfunction. And these are the discretized version of the plane waves as they should be. Okay, so this is just 1 over square root of 2 pi exponential of I kn. Okay, so they depend on a real k. Okay, so there is, that means that, again, what I have to solve here is an eigenvalue equation, and there is a continuum, there is a family of such eigenfunctions which are parameterized by k, and we know that in this case that the associated energies epsilon, they are labeled by k themselves, and they simply look, it's easy, very easy, just need to substitute this value in the Schrodinger equation, discrete Schrodinger equation, and you would get this minus 2t cos k. Okay, very simple. And of course, because of periodicity, the k here does not need really to be real, but it only takes the value minus pi plus pi. But this is just the Brillouin zone. Okay, so that's a starting point to have in mind, because later on we will try to understand what happens if you sort of add a small disorder. Okay, so it will be useful to think about it in this way. So of course the question is what happens now to that equation, which is really the guy that we are after in the presence of a Vn. Okay. Now, usually the disorder that we choose is symmetric, positive or negative. So Vn and minus Vn occur with similar probabilities. And in fact, what we usually do, instead of having a minus t here, that's a convention. We usually study the model where we just put a minus sign in front of everybody, and rewrite the following equation in a slightly more formal way, keeping in mind, if you want to connect to the original Schrodinger equation, that there has been a minus sign, sign which entered into the game. But more formally, the problem that we want to study, so that's usually the way this Henderson model is studied more formally, since Vn is positive or negative with equal probability. Well, so it's what I mean by that is that it's not very nice. I can just look at Vn or minus Vn. Eventually, the model that you really look at is the following. So it's written in the basis of where I have discretized my system, and the action of H acting on psi, so that's a vector, and the nth component of that vector is just written in this way. Okay, so and I'm writing it now in any dimension. Okay, so so I'm looking at the general dimensions, even bigger than 1. So instead of, so maybe I can just come back to that expression that I had here. So what happens in higher dimensions is that instead of having just a sum, so you see here that you have a sum, so you are summing over your right neighbor and left neighbors. And in general, what you are doing is that in higher dimensions, you will have a sum here over all your next nearest neighbors. Okay, so that comes from the discretization, of course, of the Laplacian. Okay, so the natural generalization in higher dimension is that provided you are doing this minus sign that I mentioned, is that you will generically have a sum here over all the neighbors of M. Okay, just denote it this way, psi M. So J is minus T if you want. Okay, so I did this change T to minus T essentially. And then I have this plus Vn times psi N. Sorry? There was a question? Okay. So that's the model now that we really are after. And you want to understand the eigenvalues and eigenvectors of this, of this operator H.
Sorry, I guess in the sum you meant index M instead of index N everywhere.
Yes, so this is the M. Okay. But here this is the N. So I'm summing, so M is a dummy variable indeed. That was a mistake. And I sum over all the neighbors of N, okay? Is that clear? Maria?
Yes, it is.
Okay. Fine. So again, here what this means here, these are just the neighbors of N. And you have these two terms that I already mentioned before, which are sometimes called the hopping terms on the one hand, and the on-site disorder on the other hand. So typically, what we will have in mind, one may discuss, of course, the universality with respect to the disorder and study how the properties of the system will depend on the types of disorder that you consider. It turns out that there is a quite wide universality, and for the time being, we will consider the case where this Vn here, just to fix the ideas, are just random variables, and I will consider the case where they are IID, okay, so independent and identically distributed. And one case which is widely studied is the case where they are uniform. Uniform and say uniform over, okay, minus omega by 2 and plus omega by 2. Okay. So we have these random variables, and now I need to solve this problem. Now, as I said last time, in fact, when I started my lecture on random matrices, you see that now I had an operator H initially, the Schrodinger operator, but once I have discretized it, now I have more a matrix than an operator, okay? And that means that now, so in general, the model, so this is the model that is called the Anderson model. And this model usually can be defined on a subset of ZD, okay? So with n sides. So you can think of a rectangle, or a square, an hypercubic lattice, an hypercubic box. That means of linear size L. Okay, so I will have L to the D sides on it. Okay. And in this case, as I said, this H operator is now a random matrix, or say is now a matrix. So H is now a matrix. And you see, it's easy to see that it has a relatively simple structure. This is just, so H of Mn, so this is just equal to J if M and N are nearest neighbors. Okay. And on the diagonal, you have a special value. So Vn, if m is equal to n, and the rest is just 0. Okay. Now, as I said, and that will be that was also what I had in mind before. Is just to be precise, we will consider the case where we have a box here with periodic boundary condition. Okay. So that's what I have. So you see that this matrix, I mean, if I look at it, for instance, if I look at how it looks like in 1D, well, in 1D, that would be a tridiagonal matrix, right? So I would have random numbers on the diagonal, and I would have these J, which are non-random numbers, say on the first and second off diagonal terms. Okay, so maybe it's useful just to write it how it looks like in 1D. Just to fix the idea, right? In 1D, I would have a matrix which would be something like that, right? So I will have, say, on the diagonal, I will have random numbers, V1, V2, V3, say Vn. So they are random numbers. And then if I just look at these guys there, so I will have J, J, J everywhere here. And the same just down, J, 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 J here. And basically I have 0 as well. Okay, and again, so the J's are fixed, so they are deterministic random numbers, but the VI's are random. So you see that this is indeed a random matrix, and if I want to connect this to what we have seen before or last time, you see that this is clearly a random matrix, but it is not really of the type that we discussed last time, which was basically the Wigner matrices of the GOE matrices, which were completely random. Here you see that you have some structure, okay? You have a kind of structure in the sense that they are different from GOE. Or Wigner matrices that we discussed the other day. And there are two things which, I mean, in particular are different. The first one is that there are many zeros in this matrix. Okay, so it's when n is large, eventually this matrix is essentially empty. Okay, and this is called a sparse matrix. Okay, so the matrix H is sparse. You remember that instead the GOE and Wigner matrices were full, right? For GOE matrix, I mean all the elements are non-zero. So that's the first thing, and that actually reflects the fact that we have a finite dimensional system. Okay, the reason why these guys are 0 here is because one site is not connected to all the sites, but instead only to its nearest neighbors. So that reflects, if you want, the finite dimensionality of your problem. And the other important feature that was absent, in fact, in the Wigner or GOE matrices, is that there are typically, in this model, there are typically two different scales. Okay, one which is associated to these hopping terms, which comes from the Laplacian, and they come with the J. This is deterministic, so this is the first scale. And then I have another scale, which comes from the disorder. And the typical scale in this case is omega, say if I took these VIs to be uniform random variables between minus omega by 2 and minus omega by 2 and omega by 2, then typically the strength is over the omega. Okay, so we have two different energy scales, which were of course not the case in the GOE, where they were all the same up to a factor 2, but they were not different scales, right? This is just one factor, numerical factor, where all the scales were the same. There were unique scale, basically, which was the variance of the elements. So here, and this is different from the GOE. There were two energy scales. One comes from the hopping, which is J, and the other one which comes from the disorder. And they will compete. Okay, so it's as I did in my notes, it's much better to think about it as a competition. Okay. Now, I'm not saying that what we have seen last time about the GOE matrices need to be completely forgotten. And it turns out that there are some features from GOE matrices which are also present there, and I will comment on that later on. But at least at first sight, we are dealing here with a different class of random matrices. Okay, fine. There are various remarks that we could do that I will just do like this. I just wrote them in my notes. Will not be very. I mean, will not elaborate more on that. We are dealing here with a finite matrix. Okay, it's also possible to look at what happens in the limit where you really take an infinite matrix, and where H is really an operator. Okay, so in some sense, you can also treat the continuous case, but mathematically it turns out to be more complicated. Okay, so the large n limit, if you want, can also be treated, but continuous case is the continuum case. Where what I mean is that where H becomes an operator and not a matrix is possible to treat, but more complicated. And I will not comment on that. Another thing that I want to say is that once you have defined your problem on the lattice, so I basically showed you how to define your model on Z to the D. In fact, in principle, you can define it on any type of lattice, okay, and on any type of network, in fact, on any type of graph, I should say. And in fact, that means that you can even then define it on the random graph, for instance. You can also define it on the beta lattice. Beta lattice might be actually quite interesting because it allows, as we have seen during the first, I mean, some of you have seen during the first semester, this allows to sort of study the model in a kind of mean field limit, which is quite interesting in this case. But what I want to say is that different type of lattice can be, different type of graph can be, or say the model can be defined. An arbitrary graph, and including the beta lattice. Okay, so I will not say more about that. For those of you who have thought about it, just keep in mind that this is a nice way of providing mean field description of this condition. Okay, so let's move on, and let's try to be slightly more precise about the type of observable that we might be interested in to characterize the localization properties of the system. Okay, so let's, except if there are questions, of course, but let's move on, and let's consider, or let me just describe for you a couple of important observables that are of interest. So again, the list is not exhaustive, okay, but okay, let me just, for simplicity, let's just put h bar equals to 1, okay. I'm sorry about those of you who are attached to finite value of h bar, but I'm sure they will not be too hungry with it. So what I really have to study now is simply, so let's look at the dynamics for a while. Okay, so that's what I want to understand. And of course, it's quite useful. It's quite useful to look at the eigenvectors and eigenvalues of H. Okay, so let me just denote them by V alpha and their corresponding eigenvalues omega alpha. And of course, this is an n by n matrix. So alpha is just an integer, say between alpha, between 1 and n. And of course, the basis is orthonormal. Okay, fine. Now, what is there is another canonical basis of the Hilbert space once you have discretized your Schrodinger operator, is the Hilbert space, which is generated by this basis that I will denote by I, sorry. And these are the basis of vectors which are localized on site I, okay? So I can define them rigorously, properly, but I mean, but the physical picture is simply that this state I is really localized on a given site, and it has no component on the other ones. Okay, so that means that if V alpha, if I have a state which is proportional to I, that means that it is just localized on a single site. Okay, so that's the equivalent of delta of the delta function, if you want, delta of x minus x naught in the continuum case. So what are the different natural observable that you might be interested in? But if you look at the dynamics, there is an interesting observable, which is simply the propagator. Okay, so let me just denote it as pi from I to j. And what is that? This is just the probability of observing. Okay, I will not write it, I will just say it. This is just the probability of observing my particle at site j and at time t, given that it started from site I at time 0. Okay, so this is just a probability to compute that. I mean, this is just so what is the matrix element that I really need to compute? Well, I started from the state I, so I was localized in I. Then I evolved it with my Schrodinger operator. And then I just want to compute the overlap of this state with the state localized at j. Okay, so I just compute this matrix element. And since I want to compute the probability, what I need to compute, of course, is the modulus square of them. Okay. So now, in general, it's a complicated object to compute, right? But now it's quite natural to expand this amplitude on the eigenstates of H. Okay, so let's do that. So I will just write it in this way. So that's just the sum over alpha. Okay, so I didn't do anything except inserting a closure relation with respect to the V alpha. Fine, and using the fact that that V alpha are the eigenvalues of H with the eigenvectors of H with eigenvalues omega alpha. Fine. So now I need to compute this sum square here. So what I will do is that, in fact, I can write the square of the sum as the product of two sums of this times the conjugate of it. So I will have a sum over alpha times a sum over beta. Don't want to write it, but just ask you to imagine that when I will have this double sum over alpha beta, I will basically disentangle first the terms for which alpha is equal to beta, and then the terms where alpha is different from beta. Okay, so if you do that, you just writing things. But let's see how it reads. So basically, that means that. So that's an important notion. That's why I want to write it explicitly. It's a bit long to write, but so let's look at the diagonal terms. Okay, so that's what I mean by diagonal. So I write it first. This is just that. Sorry. That's the diagonal terms. Indeed, in this term, there is not any more time dependence because I had the exponential of minus I omega alpha t times exponential of plus I omega alpha t, right? Remember that I need to compute the complex conjugate. So this guy does not depend anymore on t. And I have a second term, which is more complicated. And this is just, okay, I just write it. Maybe I should not, but. Okay. So this term here, as I said, let's mention first this guy. Okay, so this term here is something that we usually write p tilde of I to j, and it does not depend on t, right? That's the important point. Now, on the other hand, here, this sum here, you see, will be much more complicated, and basically omega alpha and omega beta will be different if alpha and beta are different, except if you have some accidental degeneracies, which I will not consider here. But what it means is that in generically, you will have a sum of highly oscillating terms here. And eventually, in the limit of large n, these oscillations will interfere destructively, and this will lead to oscillating term. And in fact, the oscillations might actually become very wild as n goes to infinity. Okay, n being the size of my system. So in other words, if I plot this, and that's quite useful to have this picture. If you really plot this quantity that is p of I, j, and t for a given I and j as a function of t, what you will observe is that it will rapidly oscillate around a kind of mean value. So in other words, if you plot this guy, that's what you will see. You might observe some wild oscillations, but typically around a value which is precisely this value that I denoted, p tilde I to the j. So that's sometimes called the diagonal approximation, the fact that you neglect these off-diagonal terms, off-diagonal in this sense. And that's very useful to compute this term only because you see it's quite simple. It's quite simple. There is one guy in particular, one quantity which is
particularly interesting, which is the PII of t, which is a kind of probability to return to the origin. So you start from I, and what's the probability that after some time t, you come back to I, okay? So that's also a measure of localization that I will not comment too much on that. So now, what else can we study? Well, there are various. You would like to say something about now the eigenvectors and eigenvalues, and to have a kind of nice representation, so a nice way of encode the properties of these quantities. Now, what we have seen last time when we studied random matrices, we have seen that there are some nice and easy characterization of the spectrum properties, which were what we call the density of eigenvalues, which in our case was this Wigner semicircle, if you remember.
I'm sorry to interrupt you. Can you please repeat? So on this plot, you just wanted to show that these oscillations will decay, or?
Yeah. So what I want to say, yeah, well, what maybe I should have.
And I don't understand. You meant that horizontal axis represents n actually, and not t, right?
Yeah. So yeah, indeed. So okay, what to say is that this is this blue line here. And this blue line is meant to represent this petit I and j. Okay.
All right.
This value around which this p of ij of t will oscillate around because of that term. So this here will cause these small oscillations that I vaguely wrote here, not very precisely. But what I want to say is that if you perform, for instance, if you perform, for instance, a thermal average over a time between t and t plus capital T, then roughly speaking, what you will get is precisely this PT of ij. Okay, so that's really this constant value around which this quantity P of ij oscillates.
All right. Yes, I just misunderstood. I thought that you were wanting to draw the same thing, but for n tends to infinity and.
Oh, okay.
Okay. Okay. So thank you.
That's really as a function of t, and one has to think that this PT of ij is a good measure of the temporal average of this quantity, if you want. Okay.
All right. Thank you.
So now, if I look, so if I want to have other types of properties related to these random operators, which is now a random matrix, as we have seen last time, a central quantity is the density of states. Okay, so what I mean by that, this is the density of eigenvalues, if you want, which in this context is called the density of states, DOS, and which is just this guy, right? This is just rho of E, and this is exactly what I call the empirical distribution last time. This is just the sum from alpha going from 1 to n. So this is interesting, of course. However, you lose completely the information on the eigenvectors. So last time when we discussed GOE, I tried to explain you that we had good reason to do that, because for GOE, because of the fact that the probability measure is invariant under the orthogonal group, that means that the eigenvectors of your matrix belonging to GOE are first independent of the eigenvalues, and second, that the distribution of these eigenvectors is quite trivial and is completely isotropic, and that means that the distribution of the eigenvectors is completely uniform on the sphere because they are normalized. So in that case, somehow the eigenvectors were not too interesting. On the other hand, here they are. And in fact, you are really pretty much interested in this localization problem. What you would really try to understand is how much are these eigenstates localized. That means that what you really, a crucial question in this localization problem is whether this V alpha here is it localized around a given site I? And that means that I have a very high probability to observe these eigenstates very close to one or two or given finite number of sites, or on the other hand, or whether it is widespread over the whole sample. So that means that one crucial information that you would like to have concerns the scalar product of the V alpha with one of these eigenvectors of this localized basis here. Okay, so that's what really is missing in this density of states, because it has forgotten completely about the structure of the eigenvectors, and that was already soon realized. I mean, it has been realized, of course, already by Anderson himself, that you really need to go beyond that observable to say something about the localization of the eigenvectors. And the first attempt to go beyond that is to look at what is called the local density of states. Which is L-DOS, okay, and which is called, okay, which now depends both on energy and the site I. Okay, so we are working still at fixed energy, if you want, in the sense that we look at the, as we did in the density of states, we are just looking at all the states with a given energy E. Okay, so I'm just summing over alpha here, but with the prescription that their energy is still equal to E. But now I want to characterize, in addition, how much these eigenvectors are close to I. So in other words, what I will weight this delta function with the scalar product of I and V alpha. And to get the probability, I need to take the square. Okay, so that depends on I. And that's much more interesting now, because it tells me how much the states of energy E overlap with I. Okay. So I get now some information, some additional information from the eigenvector themselves. So that's one quantity which is important. Now, let me just finish by a last observable, which is crucial when you study localization, and in fact, when you study disordered system in general. But maybe we had not the opportunity yet to discuss it, which is called the inverse participation ratio. So its precise definition might depend from one model to another, but its meaning is pretty universal, and this is called IPR of alpha for inverse participation ratio, and that's, so the definition is not immediately appealing, but we'll try to understand what's happening. So that's this quantity, okay? So let's try to understand what it means. So suppose that our state V alpha is localized on a given number of sites, and call this number n index alpha. Okay, so suppose that V alpha, so that's what I want to say. Basically, it should be better to write it this way. Suppose that this scalar product IV alpha is different from 0 on n alpha sites and constants over this region. Just just to fix the idea. And constant. So physically, it means that you have an eigenstate which has a support on a given region of the space, which counts n alpha different sites. Okay, typically they would be connected. That would be a connected state, but this is not necessarily the case. In any way, here I'm just having this kind of state. Okay, so I have a state whose typical extension is of the order of n to the alpha sites. So now, and I also assume that it is constant. It is basically uniform over these sites. That means that the probability to observe the particle on one of each sites is the same. Okay, so that's what it means. Now, because the states has to be normalized, it's clear that it's uniform and normalized over these n alpha sites. So that means that necessarily I must have that I v alpha is typically 1 over square root over n alpha on an alpha sites and is 0 otherwise. Okay. Again, this is because of normalization, right? Because I need to have the sum over n alpha sites of the square of this, which is 1 over n to the alpha. I need this to be 1. Okay, so I have no other option to have this normalization factor. So now, if I compute the inverse participation ratio for that state, you see, it's easy to compute. So just again to fix the ideas. So if I compute the IPR of alpha in this case, so it's the sum, again, it's the sum over I of the scalar product to the power 4. Okay, so that's in this case is just 1 over alpha to the power 4 square, sorry, so it's square root of n to the alpha to the power 4, so it's 1 over alpha squared. And you see, how many sides do I have here? I have n alpha sides. Okay, so this is just equal to n alpha. 1 over n alpha. Okay. Good. So this inverse participation ratio is used to measure the localization of the states in the following way, in the way that basically when what we will say is that when n goes to infinity, typically 2 things will happen. If I take the limit n goes to infinity, either this inverse participation ratio will go to 0. That means that here, this n alpha is proportional to n or to some powers of n, and eventually that means that it will indeed be extended over an infinite region as n goes to infinity, or it might only stay finite, and in this case, this will the measure of the IPR alpha will just give me 1 over the number of sites over which the wave function is localized, and that's the second case where it might be strictly positive. So that's how we usually define a localized vector. So it has a finite inverse participation ratio, while here in this case it would be delocalized. Okay. So these are the sets of observables that we have. This density of states, local density of states, and inverse participation ratios. And eventually, another quantity which is interesting is this propagator, if you want, the probability to be at j at time t given I started at I. This is, of course, a good measure of localization, because if you have localization, basically what happens is that if you start from a localized state, well, what will happen is that even at large time, you will stay around and you will not explore the whole system. So that means that P of I, j will be 0 for some given sets of j. While if you have extended states, well, then typically you will be able to reach any other sites of your sample within a finite amount of time. So the last part that I would like now to discuss the phase transition in the Anderson model. But since I don't have, I mean, okay, I still have, yeah, 10 to 15 minutes. I would maybe like to share my notes, if you don't mind, just to describe for you what are the phase transitions that have been shown to exist in this Anderson model, and in the light of these observables that we have discussed. Okay, so let me try to do that. I hope it will be okay. So I hope you can read or see what I'm saying. From you, this is what we have discussed so far. So I want to go to this last part, the fourth part, and analyze and say, I mean, okay, so that's where I want to. Can you see my screen, and can you see the PDF? Is it readable?
Yes, it is.
Okay, fine. So that's my model. Okay, so I wrote it in a slightly different way, which is more close to the, I mean, second quantification, if you want. So this is my operator. Okay, so this is just these are the diagonal elements, and these are the hopping terms. Okay. Again, I and j are just nearest neighbors. Is that clear to everybody? These notations. No question for that about that. Right. So again, these VIs are uniform. So let's try to understand what happens when either VI is 0 or J is 0. Okay. So let's start with the simplest case where J is 0. Okay. So J is 0 means that you don't have any hopping. You only have a potential term, on-site potential term. And it's clear that in this case, H is simply diagonal, okay? And it's diagonal in the I basis, which are the localized states. So in this case, all the states are strictly localized. I mean, in the very strong sense that the inverse participation ratio is just 1, okay? Because you remember that if you have local, I mean, typically the inverse participation ratio is 1 over n alpha, where n alpha is the extension of each of the states. Now here it's clear that they live on a single site. And in this case, they are very strictly localized. Okay, so that's all the eigenvectors do not move. And in fact, if you compute this propagator, P of ij, basically if you start at I, then you don't move from I forever. And this guy is simply delta ij for all t. So it's a very extreme case where all the states are localized, and the density of states in this case is just the density of V, right? Because the eigenvalues are precisely the VIs. Okay, it's easy to see that the eigenstates are the I's and the eigenvalues are the VIs. Great. It's very simple. Now let's look at the other limit. The other limit is probably well known to you. I mean, I'm sure many of you have done this computation. And this is the case where you have no disorder. Okay, so it's a pure hopping. Well, in this case, I have already mentioned it. I just touched upon the case in one dimension, but you can just solve it for any d, and these are just these plane waves. I mean, discrete type of plane waves, and the k alpha, because I am considering periodic boundary conditions, the k's now are quantified, and they take these values. So L is the number of sites here. Okay, it's not n, it's L here. It should be L. Okay. Oh, sorry. No, sorry. What I'm saying is that in this case, L, excuse me, L is the length of the system. Okay, linear extension, linear dimension. Okay, very good. So it's possible to compute the eigenvalues. It's very simple. In this case, this is just this sum. There is a plus sign here because you remember that we switched from H to minus H. So it's very simple. And you can even compute the density of rho of E. I mean, in the limit when L goes to infinity, the density has a I mean, it has a nice expression. I will not do it here. I mean, it's not that exciting. But what you get is that the eigenvalues are, okay, they are in between minus 2dj and plus 2dj. I mean, this is apparent on that formula. And there is some formula that you can compute. It's quite simple, but I don't want to do that. I'm sure you have done this in your solid state physics course already many times. What about the eigenvectors? Well, you see the eigenvectors, we got them here, and we said, okay, they have this nice and simple expression, but it's also clear in this case that all these guys, so the I product V alpha, you see, in fact, if I take now the modulus square, well, they do not depend on Ri anymore. So in other words, these states here are actually fully delocalized in the sense that they are actually, they have a non-zero component on each of the sides of your lattice. So these Fourier modes here, they are actually maximally localized in the sense that if you really compute the inverse participation ratio, this is just 1 over n. Okay, so typically we said it's 1 over n alpha, where n alpha is the number of sites over which the eigenfunctions extends. Here, this is the whole sample. So it's clear that when n goes to infinity, this guy goes to 0, and in fact, this is also the smallest value that they can take. Okay. Good. You can also compute these probabilities here. But in any case, it's again, you can show that if you start from I, you can do this computation. In the large T limit, well, the probability that you end up at J will be eventually 1 over n. And that's not really surprising because at the end of the day, we know that the particle should be widespread over the whole sample. So we have these two limits, right? One where I only have the disorder and the particles are extremely strongly localized. And I have this other extreme case where I have this Fourier or plane waves, if you want, discrete plane waves, where my states are completely delocalized. Now, the question is what happens when the two are competing? As I said, such a competition, in fact, only exists in d bigger than 3 or equal than 3, where you indeed have a non-trivial phase diagram. Okay, so that's the phase diagram that I wrote here. In the omega disorder, E plane. Okay, so E is the energy of the states that I'm looking at, and I'm looking at the nature or the properties of the states as a function of omega and E. Okay, so the first thing to notice is that what you can show is, and this is something that you can show by computing the density of states, you can show that you don't have any states in these regions here. That means for E, which is less, so which is on that region here, or when E is much bigger than this 2dj plus w by 2. Okay, so on the right of that line here. Okay, so that means that if you look at omega fixed disorder, the density of states will have a finite support between minus 2dj minus omega by 2 and plus dj plus omega by 2. Okay, so that's a bit similar in some sense to what we had seen on the GOE, right? So you remember that if you take the GOE, you have a finite support in this case, the density will be different, but it will also have a finite support. Now, what is quite interesting is that the nature of the states now will depend on the parameters, on the strength of the disorder and the energy, basically. And what is nice is that, say, if you look at the fixed E now, let's look at it around this direction. So I have a fixed E, and I start to increase the strength of the disorder. So when I have no disorder, I am on that line. This is the case that I discussed before, and the states are fully extended, maximally extended. So if I add a little bit of disorder, they are still extended. They are still extended in the sense that I am in that region here, where basically the inverse participation ratio goes to 0 as n goes to infinity. So that means that my wave functions, they are not anymore these plane waves. They have a more complicated structure, but still they are still extended. So I continue to increase the strength of the disorder, and at some point I arrive at that line, which is called the mobility edge. That means that if you start to increase the disorder above some point here, then you will eventually localize your state. That means that if omega is large enough, then eventually your state will become localized, and they will stay localized in a given region of states, of the space, sorry, okay? And this is something that you can get, for instance, by computing the inverse participation ratio. This is not an easy computation. That's why I unfortunately cannot really present it for you here, but that's what happens, okay? So that means that you have a very nice transition between extended states and localized states. And this is called the mobility edge. Now, what you see also is that so if you are below this omega c, depending on the value of the energy, you might actually have extended or localized states. But as soon as the disorder is above omega c, essentially all the states are localized. Okay, so you really have a transition in the sense that if the disorder is beyond omega c, all the states become localized. So that's the generic phase diagram that you would have in higher dimensions. Of course, there are various questions that you can ask. In particular, you would be interested in how is the density of states. So for instance, suppose that you fix omega, and you would like to understand how is the density of states. Is it different from what we got for the GOE, for instance? The answer is yes. I will not comment too much on that. I briefly discussed this here. This is called the Lifshitz scales. So this describes how the density of states vanishes close to the edge. There is a huge literature on that. I will not comment on that too much, or more than that. If you want, I can give you some references related to that. I just want to end this lecture on the level statistics, and to come back, in fact, to the to what happens compared to what we have seen the other day in the context of GOE. And the question is whether what we learned the other day is it interesting for localization? And the answer is yes. The answer is yes. It turns out that the GOE statistics that we have seen last time is actually describes actually very well what happens for extended states. So in fact, if you think about what I was saying before, I was saying that in this case for the GOE, well, the eigenstates, you remember I said that the eigenvectors are completely independent of the eigenvalues, and they are also completely uniformly distributed among the various components. So that means that such a state, such an eigenstate associated to GOE is actually a completely delocalized state in the sense of localization that we discussed today. And it turns out that if you look at the Anderson Hamiltonian, and if you look at the level spacing, for instance, if you look at the local statistics of the GOE, of the states of the extended states, then you will see that they are actually extremely well characterized by GOE. So that means that if you look at in this part of the phase diagram, it turns out that if you look at the what happens in that region, it's a bit slow because of this. I'm sorry. I wanted just to stick to the phase diagram. I just scrolled. In that region, okay, so in this extended part here, this is, well, I mean, what I'm saying by well, that means that if you take large matrices, and there are theorems for that, the local statistics is exactly the one that you would find for the local statistics of the GOE ensemble. That means that you would find a sine kernel, for instance, that is well known in random matrices in the GOE ensemble. On the other hand, if you look at the localized states, there the statistics is very different. And in fact, it turns out that in the localized region, the statistics of the eigenvalue. So in this phase, of course, the statistics of the eigenvectors is non-trivial, right? Because they will have some interesting structure around being centered or localized given a given region of space. But on the other hand, if you look at the eigenvalues, the spectrum is extremely simple. And in fact, it turns out that the spectrum is simply Poissonian. So that means that for localized states, you don't have any more this complicated GOE structure, but you have a much more simpler structure for the localized state. So the eigenvectors in this case are non-trivial, but the statistics of the levels is extremely simple and given simply by Poisson distribution. So if you look at the distribution between two energy levels, well, there will be typically exponential. So the moral of that is that extended states have a quite complicated structure from the point of view of their eigenenergies, while the eigenvectors are quite simple and just uniformly distributed. On the other hand, in the localized phases, the eigenstates have, the eigenvectors have a non-trivial structure, but the eigenvalues have a very simple statistics, which is simply Poissonian. And I will end up with that because it makes a link with what we did before, and also a link with what we will do next, because in the tutorial, we will actually come back to one nice properties of the GOE, and we will study what is called the Dyson-Baryon motion, where we will actually use quantum mechanics, but from a different perspective. And the idea there is to somehow in the lecture is to show how one can derive the joint law of the eigenvalues, which, as we saw today, is relevant to describe the extended states in the localization problem. So we will see a nice method to derive this joint law of the eigenvalues, which I only gave you the other day just like that without any proof. We will show that today during the tutorial, which is not very complicated, by the way. So I will just stop sharing for a while, and I will be happy, of course, to take question if there are questions. But before that, I will just turn on the lights again because it's very dark here. I'm coming back. Okay. So if there are questions, then of course I will take them. I will be happy to take them. If there are no questions, then okay, we will just come back in, say, I don't know, maybe in 10, yeah, 50, yeah, let's take 10 minutes at 10 past 4.